Hi everyone, I'm Kirsten and today I'm going to be going over local, resting, and action potentials. First, I'm going to be going over resting membrane potential. This is when a neuron is at rest and ready to send a signal down its length. The ICF's measured value is at negative 70 millivolts in this state. The neuron uses pumps to make sure there's more sodium in the ECF and more potassium in the ICF. These are both positive, but there's a negatively charged proteins in the ICF, giving it an overall negative nature, while the ECF is positive. Both the sodium and potassium gates are closed. The neuron is using pumps to transfer sodium and potassium through the plasma membrane. Next up is a local potential. When a dendrite is stimulated, its sodium gates will open and sodium will diffuse into the ICF. This causes the negative 70 millivolts to become more positive. Any positive shift is called depolarization. The sodium ions diffusing causes other sodium gates to open as well. If strong enough, the current can go through the plasma membrane of the soma and possibly to the axon hillock. All local potentials have these characteristics. They are graded, meaning they vary in magnitude. The more stimulation, the more sodium gates will open, and the more sodium ions will enter the ICF. They are decremental, meaning the current gets weaker the farther from the stimulation site, and they are reversible, meaning if the stimulation stops, the membrane will return to resting potential. And finally, we have an action potential. Action potentials follow the all or none law. If local potential is strong enough to trigger an action potential, the action potential will occur at full strength. If not, no action potential occurs. Action potentials are not graded. They are non-decremental, meaning they maintain their full strength down the entire axon regardless of distance. And they are irreversible. Once it starts, it cannot be stopped. When a local potential reaches the axon hillock, it begins to depolarize the resting membrane potential. The local potential must be strong enough to cause the sodium gates in the hillock to open and the membrane potential to reach the threshold of negative 55 millivolts to create an action potential. Once the threshold is reached, the abundant sodium gates in the hillock open rapidly. Sodium ions from the ECF diffuse into the ICF. This causes the membrane potential to rapidly depolarize that goes from negative 55 millivolts through 0 millivolts and up to 35 millivolts. At positive 35 millivolts, which is the peak value of an action potential, the sodium gates close and the potassium gates open. The potassium diffuses from the ICF to the ECF, and this causes the membrane potential to rapidly repolarize. When a value of negative 70 millivolts is reached, the potassium gates close. With both gates closed, the pumps are able to return the cations to their original locations. Here is a small graph showing the millivolt changes during an action potential. It starts at negative 70 millivolts during the resting potential, slowly increases to 55 millivolts during the local potential, and quickly spikes up to 35 millivolts during the action potential, and then repolarizes back down to a resting at negative 70 millivolts.